Welcome to our practical guide on mastering panel statistics. Today, we'll explore how to move from basic data visualization to sophisticated statistical inference. As the quote from EViews Illustrated suggests, panel data is powerful because it allows us to control for unobserved variables that would otherwise bias our regression estimates. This presentation will provide a practical guide to panel data analysis, specifically focusing on its application in EViews. Panel data combines both time series and cross-sectional dimensions, giving it more variability and statistical power. The core challenge is heterogeneity. Each cross-sectional unit, like a country or a firm, has unique characteristics. Standard OLS, ordinary least squares, on pooled data fails because it assumes a common intercept, ignoring these individual differences, represented by A sub I, which leads to biased estimates. Panel data requires handling the seams between cross-sections. This slide outlines the analysis pathway, a structured four-phase approach to panel data analysis, complemented by a roadmap and a crucial pro tip. Phase 1, exploration, involves using time series graphs, bi-statistics, and stacked analysis to understand the data's basic properties. Moving to Phase 2, diagnostics, we assess panel unit roots for stationarity and perform cross-section dependence tests to check for spillover effects between units. Phase 3, relationships, focuses on identifying economic connections through panel cointegration for long-run equilibrium and panel causality to determine predictive precedence. Finally, Phase 4, structure, employs advanced techniques like principal components, PCA, to understand underlying variance and long-run variances for robust inference. The roadmap on the right simplifies this into three main steps. 1. Visualize. 2. Diagnose. And 3. Model. A critical pro tip is highlighted. Never jump to modeling without first diagnosing cross-sectional dependence, as ignoring it can lead to biased and unreliable results. This slide provides a quick reference for selecting the appropriate econometric tests based on your diagnostic questions for panel data. First, to check if your series is stationary, you should use panel unit root tests, such as those by Levin-Lin-Chu, or Im-Pesaran-Shin, IPS. Second, to determine if your cross-sectional units are independent, which is a critical assumption for many tests, you would run cross-section dependence tests, like the Bruch-Pagan or Pesaran tests. Third, if you're investigating whether variables move together in the long term, panel cointegration tests, such as Pedroni or cow tests, are recommended. Fourth, to identify which variable drives the other in a predictive sense, use panel causality, specifically the Dumitrescu-Hurlin test. Finally, if you need to reduce the dimensions of your data, panel principal components analysis is the method to use. A crucial point highlighted is that most first-generation tests assume cross-sections are independent. If your CD tests indicate dependence, then you must switch to second-generation methods, such as PANIC or CPIS, which are robust to cross-sectional dependence. The first step in any analysis is to look at your data. A combined cross-sections plot, often called a spaghetti plot, is extremely useful. This single graph overlays the time series for all individual units. It allows you to instantly spot heterogeneous trends. For example, if one country's GDP is growing while others are stagnant. It's also excellent for identifying outliers, where one unit behaves dramatically differently from the rest of the pack. Imagine plotting inflation rates for 20 countries. A spaghetti plot might reveal that while most countries have stable inflation, around 2%, one country shows hyperinflation, with its line shooting up far above the others. This immediately tells you about a key feature of your dataset. While graphs give us a visual sense, we also need to look at the numbers. Let's examine how summary statistics can be revealing. This slide focuses on understanding the different sources of variation in panel data. We must distinguish between within variation and between variation. Within variation refers to how a variable changes over time for a specific unit, like how GDP changes for the Central African Republic, CAF, from 1994 to 1998. Between variation captures the differences across different units at a given point in time or over the entire period, such as the large difference in GDP levels between CAF and Canada, CAN. The key insight here is that standard descriptive statistics on stacked panel data can often mask the true underlying dynamics. The overall variance might be driven predominantly by the between component, meaning large differences between countries, rather than the within component, which represents changes over time within each country. This distinction is crucial for accurate analysis. We can examine these statistics using view/descriptive stats or stat by command in statistical software. Cross-section dependence, or CD, arises when the error terms of different units in your panel are correlated, meaning a shock to one unit can spill over and affect others. Mathematically, this implies that the covariance between the error terms of unit I and unit j at time t is not zero. Cov of UIT, UJT is not equal to 0. This is a critical issue because if dependence exists, standard first-generation unit root tests like Levin-Lin-Chu, LLC, and Im-Pesaran-Shin, IPS, are biased and yield unreliable results. In such cases, you must proceed to more robust methods, such as panel PCA or second-generation unit root tests that account for this dependence. EViews provides various tests to detect CD, including the Bruch-Pagan LM test for small n panels, the Pesaran-CD test for large n panels, and the bias-corrected scaled LM. You can find these tests via the command path view cross-section dependence test. Panel unit root tests are critical for determining if a panel series is stationary. We distinguish between two primary types based on their assumptions about the autoregressive parameter, rho. First, common unit root tests, such as the Levin-Lin-Chu, LLC test, assume that the rho parameter is the same for all cross-sectional units. This implies that all units behave similarly and converge at the same rate. The visual on the left shows parallel lines, representing this common behavior. Second, individual unit root tests, like the Im-Pesaran-Shin, IPS test, or Fisher ADF test, are more flexible. They allow the rho parameter, denoted as rho I, to vary across each individual unit. This accounts for heterogeneity, meaning units can have different convergence properties. The visual on the right shows diverging and converging lines, illustrating this individual behavior. The decision between these tests is crucial. Use LLC if you believe all units in your panel behave similarly, for example, highly integrated economies. Use IPS if you expect heterogeneity, for example, some countries converge, others don't, or a mix of developed and developing nations. To perform these tests, you typically navigate to View/Unit Root Tests in software like EViews and select cross-sectionally independent methods if you've already confirmed no cross-section dependence. The null hypothesis for these tests is that a unit root exists, meaning the series is non-stationary. If your p-value is less than 0.05, you reject the null, concluding that the series is stationary. Panel covariance analysis allows us to understand the correlation structure of our data in two key dimensions. Contemporaneous covariances measure the correlation between different cross-sections at the same point in time. Looking at the correlation matrix, we can see the correlations between country A, country B, and country C. For instance, the correlation between country A and country B is 0.75, and between country A and country C is 0.60. This is useful for understanding how closely different units move together. Between period covariances measure the correlation between different time periods for the panel as a whole. This can reveal patterns like seasonality or business cycles. This analysis is essential for fields like international finance, where understanding the synchronization of business cycles across countries is a central question. The goal of principal component analysis, or PCA, is to decompose the total variance in your dataset into a smaller set of uncorrelated factors. The output will show how much of the total variance is explained by each component. For example, the first two components might explain 90% of all movement in your data. In panel data with significant cross-section dependence, PCA has a very powerful interpretation. The first principal component often represents a common global factor that affects all units in the panel. Identifying this common factor is the first step in many second-generation panel techniques, which proceed by analyzing the data after this global effect has been removed. Cointegration is a powerful concept in panel data analysis. Even if individual time series, like the random walk 1 and random walk 2 shown in the graph, are non-stationary, meaning they exhibit random walk behavior, a linear combination of them can be stationary. This indicates a stable, long-run equilibrium relationship between the variables, as depicted by the two series moving together around a common long-run equilibrium path. If we reject the null hypothesis of no cointegration, it provides strong evidence that a valid, long-term economic relationship exists between the variables. This finding is crucial because it justifies the use of specific estimators designed for co-integrated panels, such as fully modified ordinary least squares, or FMOLS, or dynamic ordinary least squares, or DOLS, which provide reliable long-run estimates. The slide highlights 3 common panel co-integration tests: Pedroni, which is a residual-based test with 7 statistics, Cow, which assumes homogeneous co-integrating vectors, and Fisher/Johansen, which combines individual Johansen tests across units. Long-run variance estimation is a technical but crucial step that happens under the hood in many panel tests. Its purpose is to provide a correction for serial correlation and heteroscedasticity, which are common problems in economic time series. This is often called a hack correction. You typically need to choose a kernel, which is a weighting function. The Bartlett kernel is a popular and robust choice, shaped like a triangle. You also need to select a bandwidth, which determines how many lags are included in the calculation. The Newey West automatic bandwidth selection is the standard and recommended setting for most applications, as it chooses the optimal number of lags based on the data. For most economic data, the Bartlett kernel with Newey West automatic bandwidth is the standard robust setting. When you run a panel unit root test, the software is internally calculating a long-run variance to ensure the test statistic is reliable, even if the error terms are correlated over time. Using the Bartlett kernel with Newey West bandwidth is the standard way to get a robust result. We have now covered the main steps in the panel data analysis workflow. It's important to understand what Granger causality means. It is not about physical causation, but about predictive precedence. The test answers the question, does the past of variable x help predict the current value of variable y? There are 2 main approaches in a panel context. Stacked causality treats the entire panel as one large system, assuming the coefficients are the same for all units. This is a strong assumption. The Dumitrescu-Herlin test is more flexible. It runs individual Granger causality tests for each cross-section and then averages the resulting test statistics. This approach allows for heterogeneity, acknowledging that the causal relationship might differ across units. Panel resampling, also known as bootstrap, is a powerful advanced technique used to generate more accurate p-values. It is particularly valuable for small samples or when the critical assumption of cross-sectional independence is violated, leading to more robust statistical inference. The core concept behind it is generating critical values, especially when your data is non-normal or dependent. This is achieved through techniques such as bootstrap, which includes residual resampling and cross-section resampling. In practice, panel resampling is used in unit root and co-integration tests to obtain robust p-values, ensuring the reliability of your findings even under challenging data conditions. This slide provides a crucial look into setting up your data in EViews for panel analysis. The main image shows the Work File Structure dialog box, which you access via Proc Structure Resize Current Page, as indicated by Step 1. This dialog is where you define how EViews interprets your data. Step 2 highlights where you select Dated Panel for the work file structure type, which is essential for working with panel data. Below this, Step 3 directs us to where we define the cross-section ID series and date series. In this example, ISO code is used for the cross-section ID and YR, or year, for the date series. On the right, an interface tip emphasizes that panel-specific options, such as unit root or cointegration tests, will only appear if the work file is correctly structured with both a cross-section ID and a date ID. This underscores the importance of correctly setting up your work file from the start to unlock the full analytical capabilities of EViews for panel data. This slide provides a concise cheat sheet for common EViews commands, essential for efficient panel data analysis. We'll quickly review some key commands. First, to visualize your data, the freeze gr1 group.line panel combined command allows for graphing, specifically creating combined panel line graphs. For diagnostic testing, series.uroot ex const method equals LLC is used for unit root tests, here showing the Levin-Lin-Chu method. To test for long-run relationships, group.coint method equals Pedroni performs cointegration tests, with Pedroni being a common method. For structural analysis, group.pcomp cov equals core computes principal components using a correlation matrix. To check for cross-section dependence, you can use group.cd. Lastly, to get descriptive statistics by group, series.statby mean SD cross ID calculates mean and standard deviation for each cross-sectional unit. The overall benefit, as highlighted on the right, is efficiency. Using these commands allows you to automate repetitive tasks and save your workflow in a program file, .prg, for future replication and consistent analysis. This slide provides a comprehensive summary of our panel data analysis workflow. First, always visualize your data to understand heterogeneity and identify any unusual patterns. This initial exploration is crucial. Second, move to diagnostics by assessing cross-section dependence and stationarity, as these determine the appropriate tests for your panel. Third, test for Cointegration to identify long-run relationships and perform causality tests to understand predictive precedence between variables. Finally, refine your analysis with structural techniques like principal component analysis or other advanced research.